Okay, so in the last class we were discussing 2's complement number system. We discussed at length. Just a quick recap. Give you the number A, capital W bit number, that is in binary. If you had these bits, this is a sign bit, MSB is a sign bit, and there is a binary point here. Okay, this is a binary point. Then under 2's complement number system, its value was decimal value, decimally equivalent to this. We verified. So, I will not go into the theory again. This number, this could be 1 or 0, but now when I say decimal, you take it as a decimal number and then do the decimal arithmetic based summation. So, when I say plus is a decimal summation, okay. And then obviously, when you put I equal to 1, you are here, a w minus 2, there is a binary point. So, a w minus 2 times 2 to the power minus 1, next one 2 to the power minus 2, next one 2 to the power minus 3, like that up to here. Okay. That part, if I had this part, I know it is binary equivalent, decimal equivalent, conventionally is this much, but the sign bit is to be treated this way. Then this is the number. So, the sign bit is the, if the number is positive, then the sign bit is 0, obviously. Net thing, this is 0. So, net decimal value is what is simply we are familiar with, the decimal equivalent of this. Okay. When it is negative, I told you that sign bit is 1, then you start with the case with 1.00000, in that case only minus 1 remains, this part is 0, then 1.0000 dot then 1, minus 1 plus a little bit number, small number. So, it starts falling, I mean starts moving away from minus 1 going towards 0. Finally, 1.111111, so this is minus 1 plus some number, so a negative number of very small magnitude. So, those are the numbers covered by this. Okay. Then I also said that given a number A, its negative number minus A under 2's complement system, we said it was very simply, that is minus A is nothing but, if you consider this binary thing, complement all the bits. And add a plus 1 here. Whatever binary number you get, its decimal equivalent will be minus A under 2's complement system. That is, if A is this, minus A will be what? First this part, what is the decimal equivalent of this under my definition of 2's complement? Minus this plus this number and then one fellow 1, that is 2 to the power minus w minus 1, this binary 1. Okay. And then I said that if you are doing say B minus A, that is B plus minus A. B has a 2's complement system, minus has a 2's complement system. If you add, you do not need any subtractor basically, because minus A is nothing but this, and suppose there is another number B, that also will have similar form. You simply have to add this, isn't it? Because there is a 2 to the power minus 1 term, that is the point, there is the 1 immediately right to the binary point. Then there is a term 2 to the power minus 2, 1 bit to the right, that way. So, just compare the terms and I mean just collect those terms and go on adding, as you do in binary actually. So, you just need adder, that is all. That was a great advantage. Other advantage, I told you that if you are adding many numbers and if it is guaranteed that the resulting number will have no overflow, after all no overflow, because I missed out this point. Here it could be 1 or 0. 0 means what is the maximum number I said? 0 with 0 means positive with 0.11111 dot dot dot. There is a maximum number, that was 2 to the power minus, and minimum number is the max. I mean the minimum number is with 1 0 0 0 0. Then minus 1. This is the range. Okay. 0 1, this range should not be crossed, then there will be overflow. Okay. Then I said 2's complement had the advantage that if you are adding many numbers and if it is pre-guaranteed that the resulting sum will lie in this range, there is no overflow. then even if there is intermediate, I mean overflowing the intermediate summations, because you are summing only 2 at a time, you do not have to bother about those overflows, because final result will be correct. Okay. That is what I think I stopped yesterday. I cannot get into all the theoretical derivation and all yesterday, as I did yesterday, but that is in the net, you can see. Couple of things on this. Suppose a number A is given to you as before, that is and I divide this number by 2. What will happen? This side also have to do the same, isn't it? So, whatever I had for 2 to the power minus 1, that will become 2 to the power minus 2. 2 to the power minus 2 will become 2 to the power minus 3. This will have a 2 to the power minus 1 term, right? But then I can write this as A0 earlier was this, the power. So, now it will be one more. So, this. Okay. What is in binary? What number it represents? This is a sign bit, a w minus 1. Still, that point again this goes to the right. Whatever I had earlier here, that moves to the next point. Dot dot dot. A2, A1, A0. Earlier at this location I had A0, A1 has moved. Earlier at this location I had A1, A2 has moved, and A0 has moved further to the right. You see, the sign bit gets extended. It's called sign extension. Sign, if you divide the number by 2 under 2's complement, the sign bit, it gets extension and others get shifted progressively accordingly. If you divide further by 2, this will further move down to this side. This again it will repeat, this will all get shifted to the right. Okay. As an example, if you are not understanding, consider any number, say 0 point something, say A3, A2, A1, A0, suppose. A4 is 0, suppose. If you divide by 2, what will happen? If you divide by 2, A3 will go to, you all know this, isn't it? This binary, 0 comes, A3 goes here, A2 goes here, A1 goes here, A0 goes here, and positive remains positive, so 0. But you see 0, 0, so you can always see that 0 is extended, sign bit extended. If it is negative number, you divide by 2. Divide by 2 means, what is the value here? There is simply minus 1 plus A3 2 to the power minus 1, A2 2 to the power minus 2 plus, divide by 2, it becomes minus half, which you can write as minus 1 plus half. If you divide this by 2, this becomes minus half, which I can write as minus 1 plus half, and then this is 2 to the power minus 2, all that. So, 1 comes, 1 because of the sign, minus 1 plus half. I am not writing, I hope you understand. Minus 1 plus half, minus 1 is the sign bit, so sign remains 1, plus half, that is why 1 here. Then A3 gets 2 to the power minus 2, so A3 comes to this location. Okay. All right. Now, suppose we will be multiplying two W bit numbers, A and B. There could be W1, W2, but I am taking them to be same length. After all, in registers, you know, I mean, there is a uniformity. In any system, you know, we always have the same length, I mean, all words of the same bit length, you know. So, keeping that in mind, suppose A and B are two numbers, we will be following what is called Horner's rule. Our purpose is to develop parallel multipliers, 2's complement multipliers, which will be basically pipelining and get a systolic array kind of architecture for it. Horner's rule. You are given two numbers A binary is binary wise just these bits. Decimally I am writing it too often. Okay. Similarly, a number b is given. Once again, Pari is very unclear in all these chapters. Many things are written, non-written, not explained. Okay. Suppose I will be doing a into b. My purpose is to do a into b. First, I will look at it in the decimal domain. That means these two numbers I have to multiply. What I will do? I will keep a as it is decimally, expand b like this, and multiply. I am coming to Hodner's rule. It is a nested multiplication, chain multiplication. So, a into b will be what? A into this expression. Okay. This is decimal. Numbers can be 1 or 0, but down here in this expression you have to take the decimal. You have to decimal arithmetic is used. Okay. These distinctions you have to understand. Book does not make clear where you are doing decimal. So here it is decimal. So this you put back here, and I do the multiplication. A times this guy separately, decimal multiplication, and then a times rest of the terms. Rest of the terms always have 2 to the power minus 1 or 2 to the power minus 2 and like that. So what I do, a into, what is the next term? A into b w minus 2, okay, here first term, a into b w minus 2 and 2 to the power minus 1. A into b w minus 2, 2 to the power minus 1 I make a provision here. Next term is a into b w minus 3 into 2 to the power minus 2, out of which 2 to the power minus 1 is taken care of here. So I write, I put another bracket, put another bracket 2 to the power minus 1. Okay, very simple. And like this I go on doing. I am not showing many terms. Lastly, you will get things like this. A into b last two bits into 2 to the power minus 1, sorry, a into b1 plus a b0. Okay. From the first term I am always taking the 2 to the power minus 1 common, putting it outside. Like here I put it outside. Next time something came, 1 more 2 to the power minus 1, that I put outside this bracket. I am going there, I am doing that. So finally I will end up with this. A into b1 also come, a into b0, a into b1 and a into b0, they have only one difference in terms of 2 to the power 1 to the power minus 1. Okay, so that I keep here. So here no 2 to the power minus 1, here there is 1 now. Okay. So this chain multiplication business is called Hodner's rule. This can be implemented parallelly, it's an algorithm, but to present it to you people, I will consider a special case where just 4-bit numbers are taken. You will understand easily from that how to do it in general case, okay, because general will be very clumsy. So I will take the 4 numbers A0, A1, A2, A3, B0, B1, B2, B3, okay, to present it to you. Take W to be 4 for illustration. That means A is point here. And therefore, Horner's rule in this case turns out to be what? Minus A times B3 plus A times B2 okay. This is the Horner's rule. This thing A into B2, you expand this in the 2's complement from minus B3 plus B2 into 2 to the power minus 1. So, A into B2 2 to the power minus 1 here, A into B1 to the power minus 2. So, 2 to the power minus 2, 2 to the power minus 1, 2 to the power minus 1, A into B0 2 to the power minus 3, okay, A into B0 2 to the power minus 3, 1, 1, 1, 3, fine. This you have to implement. Now, consider first A into B0 and then A into B1 and all that. A into B0 is a decimal number, A into B0, whatever it is, and then I have to add that with A to B1, but remember there is a 2 to the power minus 1. So, this product needs to be shifted to the right by 1 and then added with this, and again that is to be shifted by to the right by 1 and then added, something like that. Okay. So, this A into A is what? Now, you replace A by, do not physically replace, but in your mind replace A, instead of A, view it from its 2's complement point of view. What is A after all? Minus A3 plus A2 into 2 to the power minus 1 plus A1 into 2 to the power minus 2 plus A0 into 2 to the power minus. Okay. So, I write down those 3 bits. This line corresponds to, this is the position for 2 to the power minus 3, 2 to the power minus 2, 2 to the power minus 1, like that. Okay. Suppose I write this, whatever I am doing, I am still in the decimal domain. I am presenting the entire thing in a tabular form, but still in the decimal domain. I have not moved to binary. All plus, everything, multiplication, all operations are in the decimal sense. The way I have done this or done this is all decimal addition, decimal products. Okay. Please keep that in your mind. It is not clear in Pari. A into B0. A into B0 means what? 2 to the power minus 1 coming late. A into B0 plus view it. Take A decimally. For your sake, I am doing it separately. And of course, I am assuming no overflow anywhere and all that. A into B0 means what? A is after all minus A3 plus this times, this is A, this times B0, isn't it? So, this reality will be nothing but minus A3 B0. This number again could be 1 or 0 only, because these bits are 1 or 0 product, and each product actually, and then you have got A2 B0 times 2 to the power minus 1, A3 B0 times 2 to the power minus, sorry, A1 and A0 . Okay. So, what is this after all? This is a decimal number, but this is a 2's complement form of one binary word. What binary word? Whose sign bit is A3 B0, not minus A3 B0. Sign bit is A3 B0, and the rest 3 bits are A2 B0, A1 B0, A0 B0. Okay. I am first making this decimal multiplication. A is this much into B0, pure decimal thing, and I am expanding. All these products are 1s or zeros, because individual bits are 1 or 0, but treated decimally here. Then I get an expression like this. This is a 2's complement expression of which binary number? A binary number whose MSB is A3 B0. That time I treat it as a binary digit. Then A2 B0, A1 B0, A0 B0. So, effectively A0 B0 this one, A1 B0, A2 B0, A3 B0. In my mind, there is a weighting factor that this line will multiply, will means when I calculate the actual value, this needs to be multiplied in the decimal sense. This is multiplied by 2 to the power minus 3, minus 2, minus 1, and the minus of this will come. Okay. I am not showing these lines, but this is in my mind, that if I really am interested in the decimal value of this binary word, I will imagine a point here, this is a sign bit, minus 2 to the power minus 1, minus 2, minus 3 and this. Okay. Here I am not showing that expression, this is in my mind. With this I have to, now this I have to shift to the right by 2 to the power by 1 and then add with this. AB1 also will be by the same token minus A3B1, isn't it? Same token, A2B1, A1B1, A0B1 with the respective weights. But before I add that AB1 thing, that is A0B1, A1, A0B1, A1B1, A2B1, A3B1, that thing, with this to be shifted to the right by 1. Or effectively, I hold it like this, the product AB1, A into B1, this I shift to the right by 1. Either you shift to the right or you shift to the left, sorry, you shift this A into B1, whatever is the 4 bit one, you shift to the left with respect to this by 1 bit, then also it is same. Okay. But before that, you need to do something that is actually it's a question of presentation. Since I am doing the decimal domain, I put a minus sign. Still I am in the decimal domain. Let me go step by step. I was actually bringing to quickly to that, coming quickly to the binary form, but that would have been difficult. So, this I am still in the decimal domain. I am still in the decimal domain. Only there is a minus sign because of this minus fellow. Only in my mind is there that okay, this position corresponds to 2 to the power minus 3, this to the power minus 1, sorry, minus 3, minus 2, minus 1 and 0. Okay. I am just writing a tabular form. I am not explicitly writing the power of 2, negative powers of 2, but the net result is written here. Next thing is AB1 as I told you, but AB1 I shift to the left. Either you shift to the right or shift to the left. Okay. So, AB1, A0, B1 is here. Okay. Effectively, if I add the 2, what I would imply then is this number plus whatever be the addition, that times 2 to the power minus 1, whatever the addition, that times 2 to the power minus 2, whatever the addition, that times 2 to the power minus 3 and then 2 to the power minus 4. So, effectively actually this is shifted to the right by 1. In my tabular form I am writing in the opposite direction, I am just shifting this, but I am not making any mistake anywhere. Actually this has shifted, because this is the power to this corresponds to the power 2 to the power 0, this is 2 to the power minus 1 now, minus 2 now, minus 3 now. This has shifted, that is why this guy earlier was having power 2 to the power minus 3, now 2 to the power minus 4. Only for drawing in a tabular form, I am holding it like this, shifting to the left. Okay. But I am always having the convention that this is my MSB location, therefore, this line, this will have the power 2 to the power 0 and therefore, 2 to the power minus 1, minus 2, minus 3 and if any 2 to the power minus 4, minus 5, minus 6 like that. Okay. There is a convention, no problem then. So, I add them. So, this much I get, I add the 2. Okay. What will be the result? Actually, just give me a minute. If I add the 2, what will be the result? That is here. Same thing I have to do. I have to do AB2 also. Okay. That AB2 I move to the left by 1 bit. okay, and add with whatever result comes out with it. So, A B2 means A0 B2 minus A3 B2. Once again, this will now have power of 0. This line will be power of 1, minus 1, 2 to the power minus 2, 2 to the power minus 3, 2 to the power minus 4, 2 to the power minus 5, simple. Okay. Whatever now comes up, this shifted to the right by 1 and minus A times B3. Earlier it was A times B3, no, A times B1, no sorry, earlier A B0, then A B1, A B2, no minus business was there for A. Here again I have A B3, but not just A B3, it's minus A B3, isn't it? So, minus A, I know what is minus A. I have told you under 2's complement negation of A is what? Complement each bit and then add 1 1. Okay. So, that result I will shift to the left by 1 bit, by sum is this, whatever comes out by this summation, whatever comes out that suppose is here, I will at this minus A B3 whatever be the 4 bit what, that I will shift to the left by 1 bit, isn't it? Yes. So, first complement the bits and then have to add a 1 here and then together it will be multiplied by that guy, what is that guy, B3. Okay. So, first just complement the bits and multiply by B3, that extra 1 I will take care little later. So, if I complement the bits A0 bar times B3, A1 bar times B3, A2 bar times B3. If you are confused, you can always take that minus A in the 2's complement form, like instead of A here, put a minus A. If you put a minus A here, this will become this, and there is 1 to the power minus 3, this way. If you find anywhere difficulty, write minus in the 2's complement form, then expand. To the minus 3 into B0, okay, like this. So, this part, this I will add here later. First I am doing only this part, minus A3 bar, by A2 bar, A1 bar, A0 bar, all by multiplied by B3 fellow and shifted 1 bit to the left with respect to the previous positions. Okay. That means, I will start here, here it will be A0 bar, yes, A0 bar times B3 last one is what? Minus, why are you forgetting this? After all, 2's complement, na? Only bits got complemented. I am writing them decimal. If it are 1, it is 0. If it is 0, it is 1. So, minus A3 bar. That is I am telling you, always write this in this 2's complement form. From here, you substitute here. So, it is now minus A3 bar times this B3. Understood? Since it is minus A, all instead of minus A3, it is minus A3 bar, minus A2 bar, A1 bar, A0 bar, that is all. And then I have got this poor fellow. This is always aligned with this fellow, A0 bar. So, here I have to add a 1, not 1 into B3. So, B3. This addition if I do, I will get the result. But then I want the result again to be in say 4 bit form, after all registers are all 4 lengths. So, this lower part will be truncated out, that I do not care. This is only a tabular form and still depend in decimal form, well minus and all those, okay, decimal form. I have to just do it in the binary domain. Binary domain means, consider this part. This number, when I put a minus this plus this plus this plus this is the 2's complement version of which binary word? A binary word whose MSB is A3 B0 Okay, no minus there. This minus comes because I am just substituting directly from the 2's complement decimal expression here. That is why the minus and plus they came. It was doing in the decimal domain. But if I have to now represent in the binary word, purely in binary domain, this is equivalent to which binary word? A binary word whose MSB is A3B0, where A3B0 is 1 or 0, but it's a binary digit now, not decimal digit. A2B0, A1B0, A0B0 is the binary point here. Okay. Similarly, for what is A times B1, this is A times B1 is a binary word whose MSB is A3B1, then the point, binary point A2B1, A1B1, A0B1, right? And I have to do this addition. So far it was doing the, I was doing it in the decimal domain, I assigned some locations, okay, to the power 0 power, to the power minus 1 and all that. But now in binary domain I have got one word of this form, one word of this form, separately, one 4-bit word, one 4-bit word. How to add them? After all, this has to be shifted to the right by 1 with respect to this. But in binary I told you under 2's complement, if you shift to the right by 1, that is if you divide by 2 to the power minus, if you multiply by 2 to the power minus 1 or divide by 2, what does happen? Sign gets extended, isn't it? So, if you take this number is a binary word, binary digit, binary digit, binary digit, the binary point here. If you divide this number by 2, that is multiply by 2 to the power minus 1 for this. Basically, this sign bit will get extended. Binary point will be here, this fellow will move again here, this will follow from first to second, second to third, third to fourth. That you add with this next binary word. Okay. So, that means in binary domain what you have to do, what I am doing now here is binary, purely in binary domain. First, the binary word I know, what is this? A0, B0, A1, B0, A2, B0, A3, B0. No minus business because it is binary, and there is a binary point here I assumed. Okay. Its 2's complement representation was this with 2 to the power 0 here, minus 1 here, minus 2, minus 3 here. Now, I am in the equivalent binary domain. There is a binary point here. This entire thing needs to be shifted to the right. I mean, you have to divide by 2. So, that means binary point, this guy will go to this location, this guy this location, this guy this location, this guy next location, and binary point will remain here. Okay. Alternatively, I can do like this, add a binary point here, no problem. Okay. So, this is my sign bit. Keeping this as sign bit, I now take A B1, that also I add with this. So, A3 B1 sign bit will come under this sign bit, A2 B1, A1 B0 and A0 B0 I will add. Just a minute, I am making a mistake. A0 B1, sorry. I am sorry, A3 B1, A2 B1, A1 B1, A0 B1. I will add. This will remain here. Pari wants this to be truncated out, he puts a box around this, I also do it. You add the two binary, remember when you add the two binary, a carry might come, that carry has to be moved here, then you add the two, make a carry may come up, carry has to be moved here and all that. All those things we do, usual things. When you add them, this result you can interpret this was is a partial product, first partial product. Partial product means what? B0 times this and B1 times this, their addition, that part is a partial product. So, partial product stands for PP. I am following Pari's notation, he gives a term partial product PP. This term, if you add the two, result is calling PP. For stage 1, it is for stage 1 and it is 0th or first bit, just a minute, 1. This guy is 0th bit, yeah. then PP, this is notation, you can give any x, y, z, anything of your choice. Since he keeps a notation and I am just following that. 1 1, stage number is 1, so PP 1 2, PP 1 3. I am assuming no overflow. So, these are sign bit get added, but nothing goes to the right. After adding these two, then you have to do the next step. Again, result has to be shifted to the, I mean, you have to divide the result by 2. That means you shift the sign bit, put earlier the binary point was here, move it here, and this sign bit will go here. And then you add with this result, next result. Next result is this sign bit, this is sign bit A3, B3, A3, B2. Yeah. You add 1 second, whatever comes, there is nothing to be added here. So, this result this also will be truncated out. Whatever you get, that is for PP2 second stage of partial product 0 binary point here. Finally, this thing. So, that means you have to again shift, divide this summation, overall summation up to this stage, as I told you, by 2 again. That means this date summation result will have to be shifted, which means binary point will move from here to here, and this sign will get extended. You do not explicitly show this, this is understood. MSB is sign bit, next is sign point. I am showing for your convenience, but no need to put dots and all that. You will filled with too many dots, and which one is the real one, which one is the leftover, you will be able to express. Okay, so far so good. Now comes the last one. Last one is tricky. Again, these two you add. Last one is what? Minus a B3. Minus a B3. Again, this represents what? Not tricky. From this represents a binary word. Sign bit is A3 B3, A3 bar B3. So, A3 bar B3, A2 bar B3, okay. This will come down, again this will be truncated out. To this, here again you add B3 for this guy. That will be final result. Okay. This is Hodner's rule. Now, I ask you to draw a DG for it. We said the algorithm, can you draw a DG? DG will take two input, one is the A input 4 bits, another B input. I tell you frankly, I know it is not difficult, but since I know, I am doing it immediately, but it may not be that easy, it needs thinking. We will derive a DG, and then after the DG we will put latches and do retiming on the DG, so that critical path is reduced and all that. Huh? You understood this algorithm, I suppose? You understood how to do it in the decimal domain, binary domain, because effectively everything has to be done in the binary domain. Decimal thing I took for correctness of the result, for correct understanding of the result. So, this has to be done in the binary domain. Okay. So, this final result I will be calling it x3, x2, x1, x0. There is no space to write here. So, reality x3, x2, x1, x0. Fine. Now, we draw the DG for this. I have the book at my hand, so I can easily see and draw. I should have put a dot here, or for nodes that he has done in one diagram. Then in a subsequent diagram he has shown the inside of the node, but I am just showing the final diagram, showing some plus I don't know what he means by this. This is notation. They all take this data. A3 sign bit give what this processor does, is very simple. B0 into A3 plus 0. I will draw it separately for completeness, but it is simply that back thing in binary domain. This input into this input plus whatever comes out, that will come out here. What comes in, that will come out here. This will propagate, this will propagate. That is all. And sorry, there is another input here. Let me draw it first. This is a carry input, because when you are adding, it is not just adding. You have to add with the any carry that is coming from another stage. You have to provide for that. So, carry input. So, I can write it separately. You give some name, say B, B prime, A prime, result what name has come, S prime, S, and C prime. C is called the carry input. A prime, A propagates, A prime is A, B propagates, B prime is B, carry propagates. C prime is C, and S prime is your AB. Please see this, AB, there is S plus AB, binary addition. S plus AB, and AB is binary multiplication, means basically what? AND gate, plus this carry fellow. These are description of the processor. Okay. So, what is this stage doing? A0, B0 propagating, A0, B0 plus 0, that result will come out, but this will be discarded actually. Discarding is done later. A1, B0, A2, B0, these 4 things are done, only these 4. Now, this was coming out, but this will be discarded. B0, A0 will be discarded, truncated out, so I am not bothered. This propagates, not 0, sorry, I am coming there. Please see what is happening. This part was computed, this will be discarded. A1 B0 will be added with A0 B1, A1 B0 plus 0, that in the initial stage there is no carry is 0 for it propagates, because there is no other summation being carried out, isn't it? Simply A0 B0, A1 B0, A2 B0, A3 B0, no addition actually, because addition with respect to 0 means no addition, therefore no carry. Okay, initial carry is 0, but then no intermediate carries. So here you see A1 B0, A1 B0 and A0 B1, A0 B1, that comes out here. Okay, there is this is A2, isn't it? A2 B0, A2 B0 result. Achha, A1, that result comes out. Carry here is again 0, initial carry is always 0. Are you understanding? This addition I am doing. This addition's initial carry is 0, nothing is coming from this side. But this addition generates a result here, it generates a carry also. So this carry is generated. That carry and these two will be added. What are these two? A1 B1, A1 B1 and A2 B0, this result and this carry, they will be added. New carry will move here, result will move here, and then your A2 B1, A3 B0, A2 B1, A3 B0, and the carry coming from this previous stage, this carry is propagating, result will be coming, and then here where am I? I computed this, isn't it? A3 B0, A2 B1, A3 B0, A2 B1. This is done. This much is done. Next is this. Next is this. A3 B0 is to be repeated. A3 B0, it was going here. A3 B0, it is repeated here. Sign extension. This is repeated here. Sign extension. So A3 B0, A2 B1 done here. A3 B0, A2 B1 done here. But when it comes to this guy, this is repeated. So this will come. This will not be 0. This will come from the same result. A3 B0, A3 B0. Okay. So that guy, this carry will be added, result will come out in this direction. So I quickly complete the other part. Next is, first I draw and then explain. So what is the next step? We added these 3, that is coming out here. These 3, this summation is discarded, this is coming out here. Then you see these two, A2 B0, A1 B1. A1 B1, this result, and here I am giving B2. A0 B2, A0 B2, A0 B2, you follow me? Again initial carry is 0. A0 B2 plus A1 B1, no initial carry, result goes here, new carry comes, then your shall I continue or shall I stop, and if you can remember I stop, what? Because I mean with the time constraint to this is difficult. I suggest that we continue from here in the next class. You just come prepared with this. I will take this with me, because otherwise I have to jump over. I mean, I want to explain slowly, step by step, all the terms, what is happening and all. I mean, okay. Thank you very much.